Welcome back. In this video, I'm going to talk about applications of differential equations, including applications in population biology, looking at silly populations like let's say a population of some cute little cats on an island, and not as silly, maybe kind of scary population of bacteria or viruses or microorganisms or human beings. And we'll also look at financial applications, financial mathematics. So starting with the scary one, the population of bacteria, we would begin with the differential equation. dp by dt is equal to k times p. So the rate of change of the population is equal to a constant times the population. In other words, the rate of change of the population is proportional to the population. This population has some initial population, p sub 0, and we're told k is a positive constant. So the differential equation has been solved. This is the model that has come out. Now we're going to fit the model to our data. It says, suppose that we start with 1,000 bacteria and we have 3,000 bacteria after 1 hour. In part A, it asks us to find k, and in part B, it asks us to find the population after 3 hours. So let's fit the model to the data. This is a very rudimentary type of example of model fitting. There's far more complicated examples, but the idea is the same. You have an expression that mathematically represents the behavior of something. Then you have some data that also describes the behavior of something, and you want to bring them together. You want your mathematical model to absorb that data and reflect that data. Once we have a fit model, we can use it to make a prediction. Like in part B, what's population going to be after 3 hours? So here, how are we going to fit this data? I'll start by looking at the initial population of 1,000. So p at 0 is equal to p sub 0 times e to the k times 0. So 1,000 is equal to p0 times e to the 0 is equal to p0 times 1. And that means p0 is equal to 1,000. And this is always going to be the case that your initial population is just multiplied in front. So you have initial population times e to the kt. So p of t is 1,000 times e to the kt. And yes, we could have inferred that directly from how the model was written down and how the information was given to us in the problem. Now we have to find k, as part A suggests. Using, we have 3,000 bacteria after 1 hour. Using p of 1. When the question really should have said after t hours. That t is measured in hours, not minutes. No dirty tricks here. So p of 1 is equal to 3,000. We want to find the value of k using that information. After 1 hour, there's 3,000 bacteria. So 3,000 is equal to 1,000 times e to the kt, or e to the k times 1. I have to replace the t with a 1. I have to replace the p of t with a 3,000. So p of 1 with 3,000, I mean. Now I'm going to divide both sides by 1,000. So 3 is equal to e to the k. And then take the ln of both sides. Ln of 3 is equal to the ln of e to the k. Cancellation law. So k is equal to ln 3. And we're technically done part A. We found it. I'm going to circle that, but we're not ready to declare victory. We have our part B. And before finding what the population is after 3 hours, before subbing in t is equal to 3, I'm going to rewrite the expression and use a trick. So we found that P of t is equal to 1000 times e to the t ln 3. I'm putting the t in front just to reduce the odds that I'm going to accidentally absorb that t into the log function. It's multiplied by the log function. It's not inside the log function. Yes, we could immediately plug 3 in here and proceed, but I'm going to show you a trick. We already did this trick. I'm going to bring the t up as a power on the 3 using that log property, e to the ln of 3 to the power of t. We're going to cancel this, cancellation law, and then we get P of t is equal to 1000 multiplied by 3 to the t, and yes, use a dot. You just use the dot so it doesn't look like 10,000 and 3 all to the t. Right, now we're going to answer the question. We're going to find P of 3. What's population after 3 hours? P of 3 is equal to 1000 times 3 to the 3. It's 1000 times 27, 27,000, which might be kind of frightening. Let's break this down. Think of what this means. We started with 1,000 bacteria. After 1 hour, we had 3,000 bacteria. So that means in 1 hour, it tripled. Growth models like this have a constant doubling time, constant tripling time. So if it tripled, and constant quadrupling time, it's telling us that it triples every hour. So after 3 hours, that means it's going to triple 3 times. After the first tripling, it goes from 1,000 to 3,000. After the second tripling, so after 2 hours, it's going to triple to 3,000, so it's going to go to 9,000. Then from hour 2 to hour 3, it's going to triple one more time. So I'm going to take the 9,000 multiplied by 3, we get our 27,000. That's the second way to solve this, is to think about what the data means in terms of doubling times or tripling times, or however much it changes by, and then apply that type of growth rate based on how much time has to elapse for the second part of the problem. Okay, another one, also bacteria. A population of a certain bacteria starts with 100 bacteria and undergoes exponential growth. That's a code word. Exponential growth means we can assume the model that was just written down for the last problem. If the population doubles every 5 hours, how many hours will it take to grow to 400 bacteria? We could answer this without writing anything down. It doubles every 5 hours. So in 5 hours, it's going to be 200. After another 5 hours, it's going to double. 200 double is 400. So that's just 10 hours. Done. 10 hours. T is equal to 10 hours. Double twice. But what if it said 500 bacteria? What would we do? Well, we can't get to 500 bacteria with some nice amount of, it's not going to be a nice multiple of the doubling time. 1 hour takes us to 200, 2 hours brings us to 400, but 3 hours bring us to 800. We've overshot the 500, so it's going to be somewhere in between the 2 times 5, the 10 hours and 15 hours. I think I misspoke. I meant increments of 5 hours. Anyway, so let's do this in a more careful approach. We have P of t. I'm just going to go right to it. 100 times e to the kt. Now fit the model. Fit data to model. Find k from P at 5 is equal to 2 times 100. After 5 hours, population doubles. So how do you double something? You multiply it by 2. So 200 is equal to 100 times e to the k times 5. So 2 is equal to e to the 5k. I'm going to take a ln of both sides. Ln of 2 is the ln of e to the 5k, since we're trying to get k out by itself. Cancellation law. Ln of 2 is equal to 5k. And then divide both sides by 5. K is equal to 1 over 5 times the ln of 2. Now I'm going to write down the exponential model again with that particular value of k. So p of t is equal to 100 times e to the t over 5 ln 2. Just putting the t over front with 1 over 5. Don't want to put it back here because it'll increase the odds I'll do something wrong, like absorb it into the log function incorrectly by multiplication. I do want to absorb it in the log function by bringing it up as a power though. So I'll do that in the next line. P of t is equal to 100, oh not 1000, 100 times e to the ln of 2 to the power of t over 5. Now we can use the cancellation law, and we get maybe not a nice looking expression to you, but it's pretty beautiful to me. 2 to the t over 5 times 100. So we fit the data, or fit the model to the data. Now find t needed to get p equals 400. So I'm going to set 400 equal to the right hand side and solve for t. So 400 is equal to 100 times 2 to the t over 5. So 4 is equal to 2 to the t over 5. And we can use logs if you want. You can log both sides. Ln of 4 is equal to ln of 2 to the t over 5. So ln of 4 is equal to t over 5 ln 2. Multiply both sides by 5, divide both sides by ln 2. So t is equal to 5 ln 4 divided by ln 2, which is 10. It's 10 because you can write ln 4 is equal to ln of 2 squared. Bring the 2 down in front, so you have 10 ln 2 on top, ln 2 in the bottom. Ln 2's cancel, you're just left with a 10. I'll show you a second way to do this. This goes back to how we started solving for an x trapped in an exponential expression. If it's possible, you set the bases the same. So 2 to the 2 is equal to 2 to the t over 5. Thus, if the bases are the same, the powers must be equal. 2 is equal to t over 5. So t is equal to 10. And these methods were a lot more work than just thinking about doubling twice. How long does it take to double twice? If doubling once is 5 hours and the doubling time is constant, well, 10 hours. All right, how about this? 1,600 bacteria. So we had 100. And then after 5 hours, we have 200. After 10 hours, we're going to double again, go to 400. After 15 hours, we're going to 800. After 20 hours, we have 1,600. So that's the answer. T is equal to 20. Very easy if you think about it in terms of constant doubling time. But let's go ahead and do this algebraic way. But not, I'm not going to redo everything from scratch. We got this model at the end. P of t is equal to 100 times 2 to the t over 5. I'm going to start there. It's all the same work. It's all the same numbers. We found, I'll call this method 2 over here. Slightly misleading because it's not always going to be a beautiful number like 1600. It might be a less beautiful number like 1800 or 1400. So we found earlier that P of t is equal to 100 times 2 to the t over 5. Set P equal to 1600 and find t. So 1600 is equal to 100 times 2 to the t over 5. Divide both sides by 100. So 16 is equal to 2 to the t over 5. And we have an easy way to do this. Replace 16 with 2 to a power. 2 to the power 4 is equal to 2 to the t over 5. So 4, the power on the left, has to equal t over 5, the power on the right. Cross multiply by 5, so t is equal to 4 times 5, which is 20. Same thing we got on the right hand side. And then the second approach, log both sides. So the ln of 16 is equal to the ln of 2 to the t over 5. Bring the t over 5 down. Ln 16 is t over 5 times the ln of 2. And then multiply both sides by 5, divide both sides by ln 2. So t is equal to 5 ln 16 divided by ln 2. And we could simplify. We could write 16 as 2 to the power 4. Bring the 4 down, because it's inside a log function. 4 times 5, 20. So we have 20 ln 2 divided by ln 2. Ln 2's cancel. We just get 20. All right. So let's look at what's changed in the problem. Start with 100 bacteria, exponential growth, population doubles every 5 hours, all that's the same. Now it's asking how long ago was the population equal to 25 bacteria? I'm going to solve this one mathematically first, and then we'll go back and think about what it means. So from before, had P of t is equal to 100 times 2 to the t over 5. Set P equal to 25 and find t. So, I mean, it's really, I don't want to proceed writing stuff down without at least pointing out that we started with 100 bacteria and now we have 25. So this is not a shrinking population. This is looking in the past. We're looking at what was there before this measurement. So backwards in time, that would mean negative time. We'll see what comes out of the model. 25 is equal to 100 times 2 to the t over 5. Let's divide both sides by 100. So 25 over 100 is equal to 2 to the t over 5. That's 1 over 4 is equal to 2 to the t over 5. We can write 1 over 4 as 1 over 2 squared. 1 over 2 squared is equal to 2 to the t over 5. And then we can bring that up as a negative power. 2 to the negative 2 is equal to 2 to the positive t over 5. Now we can set the powers equal to each other. Negative 2 is equal to t over 5. Thus, t is equal to negative 2 times 5, which is negative 10. So this was 10 hours ago. 10 hours ago. Let's think about this. At t equals 0, we have n, or I should say p. I'm starting introducing new letters. P is equal to 100. And if we go forward in time to t is equal to 5, the population doubles, and we get a population of 200. If we go again another 5 hours in the future, it's going to double again. We're going to go to 400. If we go one more time, go to T15, our population is going to be 800, etc. Now what if we go backwards? To t equals -5. Well, doubling, if we go in jumps of 5 forward to double, going in jumps of 5 backwards, we're going to undouble. Undouble. I gotta write that very close, very carefully, because it's not a word. Maybe it's not a word. I don't even know. I don't care. Undouble. So how do we undouble 100? Well, just divide it by 2. So you undouble something, divide it by 2. Doubling is multiplying it by 2. So you want to undo the doubling. Do the opposite of doubling. So p is equal to 50. Well, if I undouble it again, I'll get my 25. And that's what the math told us. The math tells us that if t is equal to -10, we will get a population of 25, undoubled twice. Okay, and all the data is the same, and now it's asking, instead of asking us for a certain time at which something happens, it's asking us what would the population be after 2.5 hours. So let's go ahead and do that. That's half of a doubling time. So maybe it's only about 50%, right? Because it's half, like the doubling is an increase of 100%. We have half of the doubling time, so maybe it'll only go up half of 100%. Sound reasonable, right? Let's see what happens. So we found P of t is equal to 100 times 2 to the t over 5. We want to evaluate this at 2.5. So 100 times 2 to the power of 2.5 over 5. So that's 100 times 2 to the power of 1/2. So 100 times the square root of 2. Well, that's not 150. I'll tell you that for sure. Well, what is it? It's approximately 100 multiplied by 1.414. Square root of 2, type it into a calculator, 1.4145. I don't know if it's 1.415. I can't remember. It doesn't matter. It's around this. It's close to this number. So 141. It's less than 50%. Now 100 root 2 is our answer. $141 is not our answer. Okay. So related example, Instead of bacteria, it's cats. We have 100 cats on Cat Island. The cat population will double in 5 years, assuming exponential growth. How many cats will be on the island in 25 years? I'm going to first figure out what the answer must be using logic, and then we'll use math. So we're starting with P equals 100, and then we go 5 years, doubling every 5 years, so we're going to have 200. And then we're going to go 5 more years, so that'll be total 10 years. So P is equal to 400, it'll double again. And when we start running out of space if I write it like this, so let me go back up here, write a little bit more compact. P is equal to 100. Or I'll do a table, maybe. So time on that column, population on this column. And every time we do a jump, we times 2. So population was 100. At time 5, it's going to be 200. Just a different way to write it. At time 10, it'll be 400. At time 15, it'll be 800. Time 20, 1600. At time 25, 3200. That's how many doubling times we have to go to get to 25 years. So we know that the answer has to be 3200, but let's build it from scratch. Our population as a function of time, P of t, is going to be our initial population times e to the kt. We find k is equal to 1 over 5 1, 2. Dot, 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 etc. We already did this. 100 times 2 to the t over 5. Right? That's the model we had over here. It's the same data we have except for the final part of the question. Bacteria, cats, math doesn't care. If it's an exponential growth model, exponential growth type situation, then it doesn't matter what the organism is. Okay, so let's find P evaluated at 25. It'll be 100 times 2 to the 25 over 5. So 100 times 2 to the power 5. 100 times 32, 3200. It matches. How many years will there be 800 cats on the island? So 800 is equal to 100 times 2 to the t over 5. 8 is equal to 2 to the t over 5. We can write 8 as 2 to the 3 and then set the powers equal. 3 is equal to 2 to the 5. Thus, t is equal to 15. You also go look at this table over here. There's your 15 there to get to 800. Just recycle that. How about 1,000 cats? All right, well, P of t is equal to 100 times 2 to the t over 5. So 1,000 is equal to 100 times 2 to the t over 5. Divide both sides by 100. 10 is equal to 2 to the t over 5. And we have a problem now. Problem. 10 does not equal 2 to a nice power. I mean, 3 is close. 2 to the power of 3 is going to give you 8. So it's a little bit larger than 3. 2 to the power of 4 gives you 16, a lot larger than 10. So it's probably closer to 3 than it is to 4. But, I mean, we're going to get an exact answer by logging both sides. The ln of 10 is equal to ln of 2 to the t over 5. So ln of 10 is equal to, bring the t over 5 down using that log property that has gotten a lot of mileage in this course. Now I'm going to multiply both sides by 5 and divide both sides by ln 2. So 5 ln 10 over ln 2 is equal to t. And that'll be your answer. Three-point something. The calculator would tell us what exactly that 3-point something is, but it has to be 3-point something. How about what was the population of cats 10 years ago? So I'll do this one math. The math, p of t is 100 times e to the, not e times 2 to the t over 5. So p of negative 10, now be careful, 10 years ago, this is the past. In the past, negative time. It's negative time with reference to 0 being right now. So 100 times 2 to the negative 10 over 5. 100 times 2 to the negative 2. So 100 times 1 over 4. Bringing that negative power down as a positive power. And 2 squared being 4, which is 100 over 4, 25. Or we can undouble twice. Undoubling once brings us to 50. Undoubling again brings us to 25. We're undoubling twice because 10 years ago was 2 undoubling periods. It's a doubling period of 5. All right, and we'll continue with finance examples in the next video.